Welcome to the third lecture of week 4. In this lecture, we will further our discussion of sequences. Last time, we talked about how to prove a sequence converges. This time, we will talk about how to prove a sequence diverges. Let's start by recalling what we need to do to prove that a sequence diverges. The statement is, for any potential limit point y in R, there is some threshold epsilon so that no matter how long we wait, there will be a later time such that the sequence will jump back out beyond the threshold distance. It turns out, frequently, one can get away with proving something even stronger. Notice that the condition we're trying to verify to show that the sequence is divergent is something that looks like for all something, there exists something, for all something, there exists something. Something hopefully you remember from your intro to proofs class is that swapping the outermost for all with the there exists will get you a stronger statement. The idea behind this is that a for all followed by a there exists says that given a point y, we're allowed to adjust our epsilon based on the given y to achieve the desired result. If we swap it so that there exists come first, we will be trying to prove that there is a universal epsilon that always works regardless of what y was chosen. From this, we see that the version with the there exists on the outside is stronger, in that if we can prove the statement using a universal epsilon, then we can certainly also prove it if we are given the additional flexibility to modify our epsilon to suit the given y. We can just choose to not make any modifications. But the other way doesn't work. If our goal is to prove a statement using a universal epsilon, but we can only prove it making use of the flexibility to choose epsilon based on y, the more stringent requirements are no longer met. So this is a one-way street. To implement this strategy, we can try to prove that for our sequence, there is in fact a universal epsilon such that no matter which y and n you picked, there is always a later small n at which the term x sub n is more than, epsilon distance away from y. What benefit do we get from trying to prove a stronger statement? You may worry that this makes the problem harder. But in this particular case, where we're trying to prove that a sequence diverges, this potential difficulty is usually more than compensated by the fact that it is easier to solve the problem when we can forget about y and just focus on what the sequence is doing. We will be giving some examples of how this works today. Let's change tack slightly and talk about a property of convergent sequences. Namely, a convergent sequence has only one limit. We will see later on how this fact can be used to prove some sequences must diverge. Let's prove this theorem. We will show that if y and z are distinct points, they cannot both be the limit to a sequence. So we take 2 points and set epsilon to be 1/2 the distance between them. It is impossible for an x sub n to be within epsilon distance of y and of z at the same time. This we have the triangle inequality to thank. We can write y minus z as y minus x sub n plus x sub n minus z. Applying the triangle inequality, we find twice epsilon is less than or equal to the distance from x sub n to y plus the distance from x sub n to z. Where both distances strictly less than epsilon, they cannot sum to a number that is at least 2 epsilon. So at least one of them is more than epsilon. So it is not possible for the sequence to converge to both y and z. We can prove this step by contradiction. Suppose the sequence does converge to both values. For the epsilon we have chosen, there is some n which may depend on y, so we write it n sub y, such that for any later index than n sub y, the terms of x is within epsilon of y. Similarly, for any later index than n sub z, the terms of x is within epsilon of z. Then, if small n is greater than the larger of n sub y and n sub z, then both bounds must hold, showing that the term x sub small n is within epsilon distance of both y and z. This contradicts the result of step 3. So how does this theorem help us prove divergence of sequences? If a sequence looks like it wants to cluster around two distinct values, then neither can be the limit. And in fact, using this, we can show that the sequence must diverge. An example of one such sequence is shown in the animation. It doesn't matter if the sequence visits points that are not in the two clusters. As long as we can guarantee that the sequence will keep visiting both clusters, the argument will work. To give an example, consider the sequence alternating between -1 and 1. Let's choose epsilon to be 1/2. Remember, we are working using the idea that we will choose a universal epsilon that works for all y. The 1/2 is chosen because it is less than half the distance separating the two clusters. In our example, the two clusters are centered around 1 and -1, so any epsilon less than 1 would do. Let y be a real number. This y is arbitrary. We first use the triangle inequality to show that the distance from y to the two clusters add up to be at least the distance between the clusters. 2 is the distance between the clusters. This is the distance between 1 and -1. We can rewrite that as the absolute value of 1 minus y plus y minus -1. The triangle inequality shows then the distance from y to 1 plus the distance from y to -1 add up to at least 2. Now, let capital M be arbitrary. Remember that we need to allow this in order to prove that the sequence diverges. Consider the indices twice capital N and twice capital N plus 1. The first is an even number, and the latter is odd. So the terms of our sequence corresponding to the two indices are +1 and -1, respectively. So we can substitute them into the result of step 3. This shows that the distance of y to x sub 2n plus the distance of y to x sub 2n plus 1 add to more than 2. In particular, at least one of the two must be more than epsilon, which we recall is set to 1/2. So we can choose our small n to be the one that gives the larger distance. This way, we have accomplished our task. We have found the universal epsilon such that for any potential limit y and any index capital N, we can find some index small n, which in this case being twice capital N or twice capital N plus 1 is certainly bigger than capital N, such that the distance of y to x sub small n is at least epsilon. This is exactly what is required to prove divergence. Now let's give another property of converging sequences. A convergent sequence is necessarily bounded. Bounded here means that the set of all the values the sequence outputs must collectively be bounded above and below. This can be captured in saying that there is a number m such that it is bigger than the absolute value of every term in the sequence. We can prove this theorem. First, we set y to be the limit. We can do this because the hypothesis of the theorem asks the sequence x to be convergent. Excuse me. By the definition of convergence, we can find a natural number n such that for every index small n bigger than n, the distance between x sub n and y is no more than 1. Here, the number 1 is playing the role of the epsilon in the definition of convergence. Applying the triangle inequality, this means that for every small n greater than big N, the absolute value of the term is no more than the absolute value of the limit y plus 1. So we have shown that for every term that is far enough into the future, the term is bounded. We still have the terms before the nth term to deal with. Luckily, no matter how big capital N is, there are no more than n different values outputted by x sub 1 through x sub big N. So, the set of their absolute values is a finite set of numbers, which we've already learned must have a maximum. So, based on this maximum and the bound provided in step 3, we conclude that for every natural number, the corresponding term can be bounded above by the number m, which is essentially the larger of the upper bound for the finite set below capital N and the upper bound for the infinite set beyond capital N. This shows the theorem. Next, we discuss how to make use of this theorem for proving that a sequence is divergent. Since the theorem states that a property, namely boundedness, is inherent to all convergent sequences, by considering the contrapositive, we get the following corollary. If for every m positive, there exists some natural number n such that the absolute value of the term x sub n is bigger than m, then the sequence diverges. The hypothesis is the negation of the boundedness statement, and so it describes the unboundedness of this sequence. So the corollary can be read as saying that every unbounded sequence is divergent. To illustrate the use of this theorem, let's look at the sequence where the nth term x sub n is given by minus 1 raised to the power n multiplied by n. To prove that this sequence diverges, we start by setting m to be an arbitrary positive number. Using the Archimedean property of the real numbers, we know that there must be some natural number n that is greater than m. Since n is the absolute value of x sub n, we conclude that with that n, we found using the Archimedean property, we found an element of the sequence that has greater absolute value than the starting m. Applying the corollary, we now see that the sequence diverges. That's it for this lecture. See you next time.